Hey guys, Ms. Peterson here. So today we're going to be going through and finishing a lecture that we had actually started in class, the Titrations and Buffers Note Set 2. We already talked about how to tell if a salt is acidic or basic and write hydrolysis, and we're on how do we create buffer solutions. We're also going to be looking at how we choose an indicator for a titration and look at a couple other uncommon titrations that aren't as used as our strong base weak acid or our strong and strong that we've already talked about, but you might run into on occasion. So let's start with creating buffer solutions. Buffer solutions are always prepared from pretty dilute solutions of weak acids or bases. In order to decide which weak acid, we look at the pKa value, typo in the notes, and compare it to the pH. We want the pKa to be close to the desired pH. That'll give us the most flexibility in our buffer and have it be a better buffer over a greater range of pHs. And remember, whenever we're dealing with buffers, we're going to be working with our Henderson-Hasselbalch equation. pH equals pKa plus the log of your A minus of your conjugate base over your acid. Okay, we drop the base over the acid. Okay, so in this practice problem, we're going to make one with acetic acid. Acetic acid is actually vinegar. It is HC2H3O2, I believe. Okay, and then we have sodium acetate, which is NaC2H3O2. Okay. Because C2H3O2 is kind of long to write out, I'm going to simplify this and just call our acetic acid HA for acetic with a hydrogen, so it's an acid. And then remember, ionic compounds like sodium acetate will dissociate completely in water. So what's actually going to be in a solution of sodium acetate is our Na plus and our C3H3O2 minus. Okay, so this right here, that's the ion that's creating our buffer. It's the conjugate base of acetic acid. Okay, and for our purposes right now, I'm just going to call that A minus. Okay, acetic acid without the hydrogen. It has a sodium instead. Okay. Other information that we need to know, the Ka of acetic acid is 1.8 times 10 to the negative 5. Okay, now it wants to know the ratio of acid to conjugate base we need to maintain the pH at 5. Okay, so it's looking for this ratio right here. Okay, so we want our pH to be 5. We know our Ka. Let's go ahead and find our pKa. pKa, remember, is the negative log of your Ka value. So I type into my calculator negative log of 1.8 times 10 to the negative 5, and I get 4.744. Okay, so 4.74. Okay, now all it is an algebra problem. Okay, we want our pH to be 5. Our pKa is 4.74 plus the log of our A minus over HA. Okay, so let's solve for that ratio. Minus 4.74 minus 4.74. So we have 0. That's a 4. 0. Yes, I need to use my calculator for this. 0.26 equals log of A minus over HA. To undo a log, you take 10 to that power. So we'll do 10 to the 0.26, 10 to the log. Those cancel each other out. 10 to the 0.26 gives me 1.82. equals log, oops, sorry, the log got canceled out, equals A minus over HA. Okay, so we know my ratio of A minus to HA must be 1.82 of A minus. You can kind of picture it like over 1 here. And it's totally fine to use the decimals for this. We could put it in fraction form. I think my calculator has a button for that. Is it that button? No. But you could put it in fraction form and get like a 6:4 ratio or whatever it is. I think 0.8 in decimal is 4/5, so it'd be 1.4 to 1, or no, something like that. But it is fine to leave it as you would need 1.82 to 1 of your A minus over HA, aka 1.82 of your sodium acetate to 1 volume of your acetic acid. And that would make the pH of your buffer solution 5. Okay, cool? Okay, cool. Let's look at this one. A chemist needs a solution buffered at 4.30 and can choose from the following list of acids and their soluble salts. Okay, so if we want a buffer, we want the pKa to be as close as possible to the pH. So let's find the pKa's. So what I'm doing is I'm taking the negative log of each of these Ka values to get my pKa's. For chloroacetic acid, negative log of 1.35 times 10 to the negative 3. 2.87. For propanoic acid, negative log of 1.3. 4.89. Okay, benzoic acid, negative log of 6.4 times 10 to the negative 5, 4.19. And hypochlorous acid, .46. Okay, so which one of those numbers is closest to 4.3? It is benzoic acid. Okay, that is our winner. Okay, so that's going to be it. That one's going to need the smallest adjustment from our pH equals pKa plus log of our base over acid. Okay, that's going to need the smallest adjustment from this term. Okay, okay, this is important. Okay, when A minus equals HA, okay, then this term, if you have the same thing divided by the same thing, is 1. Okay, and go ahead, check it on your calculator right now. The log of 1 is 0. Okay, it is 0. So that is what creates that pH equals pKa. Now, you could do what we just did in the previous problem to solve for the exact ratios you would need here to get a pH of 4.3, but that's something very important that you need to know. When the concentration of the base equals the concentration of its conjugate acid, when these are equal, that's a 1 here, the log of it's 0, so the pH equals the pKa. And that's how we can decide on the best one just by looking at their pKa values. Okay, cool. Okay, cool. Now let's talk about indicators. So far in this class, we've used universal indicator, we've used phenolphthalein, but there's a lot of different indicators out there. We are always going to want to choose an indicator with a Ka near that of the acid that we're changing, because that's when it'll change color. Okay, the color, the pH that indicator changes at is called the endpoint. And what we want the endpoint to be at the equivalence point. Okay, because the equivalence point is that slope in our graph when the pH changes the most with just a little tiny bit of our base added. Okay, we want that to be when the color changes as well. So in this one, it says use the table below to determine which indicator would be best to use in a titration of ammonia, NH3, with hydrochloric acid. Okay, hydrochloric acid is a strong acid. So we're going to focus on the weak base of ammonia here. Okay, because the HCl is going to ionize completely. It's this guy that we're going to be having to figure some stuff out with. Okay, so ammonia. Let's find what its Ka value is. I don't have it up on the computer right now, so I'm just going to open up another tab. Oops. Search it over here when I was looking for something else for physics. But let's look for the Kb of ammonia. Or actually, we want the Ka. It'll technically be the Ka of ammonium. Okay, there it is. Ammonia's Kb is 1.8 times 10 to the negative 5. Okay, so let me get back. Messing this all up right now. Okay. The Kb of ammonia is 1.8 times 10 to the negative 5. But I said you need one with a Ka near that. So to find the Ka, it's going to be that magic number, the ionization of water, 1 times 10 to the negative 14, divided by our Kb value, 1.8 times 10 to the negative 5. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. My Ka value is 5.55 times 10 to the negative 10. My table here gives me pKa's. So let's find my pKa of ammonia. Okay, so negative log of that answer I just got, and I got 9.25. So which indicator is going to be best? Hey, guess what? It's our favorite one, phenolphthalein. Okay, because those ones have the most similar Ka and thus pKa values. Okay, cool. Okay, cool. Last but not least, let's look at some uncommon titrations. Okay. See how this curve has a slight change in pH, and then there's just a little inflection point. That's the equivalence point, and that's what it'll look like if you try to titrate a weak acid with a weak base. If they're both equally weak, that little inflection point where the equivalence point is will be at approximately 7. If you have a stronger weak acid or weak base, that means a stronger, think higher Ka, thus more of them ionized, that produces more H plus in solution. The pH is going to lie toward that stronger ones because strong always wins. The problem with these is you don't have that clear inflection point like you have on when you're doing a titration involving at least one strong acid or strong base. Okay, we're used to curves that look like this, and then it has a strong inflection point, and so we're able to clearly see that. That's not the case for weak acid, weak base. That's what makes these difficult to do, and thus it's rarely ever done. But what is done is polyprotic acid titrations. So if you look at an acid like H3PO4, phosphoric acid, it has 3 protons it can donate. So when you titrate it, you're going to titrate off that first proton, okay? And you'll get an equivalence point there. And then you're going to titrate off that second proton, and then that third proton, which is going to create a curve that kind of looks like this. Okay, we're buffering. Okay, all of those first protons are gone. Okay, and then we're getting to a new buffer region with a new acid and conjugate base. And then those are gone, etc., etc. If you kind of want to picture this, we're first going from H3PO4. Okay, it is a weak acid. So it'll lose one of its H pluses, and what you'll be left with is H2, PO4 minus, okay, because it lost a proton, which has a positive charge. Okay. Then, eventually, that H2PO4 minus is going to lose another proton, okay? So you're going to have H and then H, PO4, 2 minus, okay? And then that one is going to lose a proton. And that's when you get left with that polyatomic ion phosphate that we all know and love. Okay, but there's 3 steps to that titration, which can make things a little bit complicated, especially when doing calculations. So let's go ahead and look at that practice problem. Given that Ka1, so that's the titration of the first proton, is 5.9 times 10 to the negative 3, and Ka2 is 6.0 times 10 to the negative 6, calculate the pH after titrating 70 milliliters of 0.1 molar H2SO4 with 50 milliliters of 0.10 molar KOH. Okay, so first let's just go ahead and write the reaction that's going on here. We have our H2SO4, okay, reacting with KOH. Okay, this is a diprotic acid, so it has 2 hydrogens to give up. Now, the products are always salt and a water. So if I have 2 hydrogens here, okay, they're going to react with 2 hydroxides. We're going to need 2 hydroxides from them to form those 2 molecules of water. And our salt, SO4, has a negative 2 charge. K is plus 1, so it'll be K2SO4 as our salt. Okay, so that's what's going on here. Now let's think about the calculations and what we have. We had 70 milliliters of 0.1 molar H2SO4, so 0.070 milliliters, or liters, sorry, of 0.10 molar H2SO4. And we've mixed that with 0.5050 liters of 0.10 molar KOH. Okay, so let's go ahead and do real quick and convert those 2 moles because we want to see what we have going on in our beaker. So again, you just multiply the liters by the molarity and you get, okay, so right now we have 7 times 10 to negative 3 moles of H2SO4, and that's reacted with 5 times 10 to the negative 3 moles of our KOH. So which one here is our limiting reactant? Well, it's not 1-to-1, so we have to give a little bit more thought to it. Okay, I need 2 of these for every 1 of these. So this is definitely going to be our limiting reactant. Okay, how much of it is going to react? 5 moles of it, all of it. Okay. Now, because it reacts, you need 2 of these for every 1 of these. Okay, you can see this is kind of our minus 2x from our table. So when we have 5 of these reacting, we're only going to lose 2.5 of these. Okay, we're only going to lose half as much. Okay, so minus 2.5 times 10 to the negative 3 moles of our H2SO4. Okay, so we still have 4.5 times 10 to the negative 3 moles of our H2SO4. Okay, so we have to think about this real quick. Have all of those first protons gone away? Okay, well, we're still pretty acidic. Okay, if we still have this concentration, there's still quite a bit of acid there and not a lot of base. So we're going to be in that first buffer region. Okay, we're still going to be removing that first hydrogen from the H2SO4. Okay, this one Okay, if remember you can relate pHs and Kas. This would occur about pH 6. Okay, and we still have about 10 to the negative 3 moles of acid. We're still about pH 3. So we're going to be looking at our Ka1. Okay, this is a weak acid. What do we do with weak acids? We set up a rice table. Okay. Now we also are going to need, in our rice table, we have our molarities. Okay, so make sure you have this down. Instead of redoing the rice table over here, I'm just going to do it right under this reaction. Okay, but do not lose that number of moles of H2SO4 that we have. Okay, times 10 to the negative 3. We need that, though, for our rice table. It's always in concentration. That's ugly. We're just going to trash that, and I will rewrite it. Okay, 4.5 times 10 to the negative 3 moles of H2SO4. We want the molarity of it for our rice table. Okay, so we divide it by how many liters we have. We have 70 milliliters plus 50 milliliters. So that is 120 milliliters, aka 0.120 liters. So divided by 0.120 liters, I plug that into my calculator, and I have 0.0375. 0.0375 moles of that. Okay, all of this is reacted. Okay, so we don't need to worry about it. We're just focused on our H2SO4. Okay, it's going to be what's controlling the pH. So we can simplify the reaction down to that H plus and that HSO4 minus. Okay. Again, we're going to assume none of this. Okay, we're going to lose X amount of this and gain X of this. We can assume that X is going to be really small so that at equilibrium, the concentration is still going to be about 0.375, okay, plus X and X. We plug that into our Ka expression, Ka, and this is going to be Ka1 equals our concentration of H plus times our concentration of HSO4 minus over our concentration of H2SO4. Okay, plug in our values. I'm going to save room because I can't write very small on here. So 5.9 times 10 to the negative 3. These are both X, so X squared over 0.0375. Okay, and then we do some math. 5.9 times 10 to the negative 3 times 0.0375. Okay, and we get that equals X squared. So then I'm going to take the square root of that answer, and I get an X of 0.0149, which is my concentration of H plus. To get the pH, negative log of that, and you get a pH of 1.83. Okay, which is still very much in getting off that first proton, so we're totally good here. Okay, cool. Okay, cool. I want you guys to try the other one on your own, and we will go over it in class.